So for the relative intensities, we need U0, and now we have it. And then we need U prime at the power of 2 for each direction, the time average of that. So first of all, we need to calculate the turbulent fluctuation for each direction using this equation. So we know the instantaneous velocities, we know the mean velocity, so we can calculate U prime. For each time. So basically we can create here 3 other columns. So where we have U prime, V prime, meters per second, and W prime. So this will be the difference between instantaneous velocity U minus the mean velocity capital U. In order to pull it, then we need to lock the number 2. So I'll put a dollar before 2. In this way, I can pull it in the vertical direction without keeping constant the mean velocity. So first of all, I can pull it on the right side, so that I'll get also the turbulent fluctuation for all velocities components, and then I should pull it in the vertical direction up to the last time available, which is 1 second. So right now we have 3 new columns where we have the turbulent fluctuation in the X, Y, and Z directions. So now we can also verify that the theory is right, so that the time average of this turbulent fluctuation is 0. Because we know that when we take the time average of instantaneous velocity, basically what's happening is that this component is 0. So you get rid of that. So let's check that everything is correct. And we can do it here. For example, we calculate the average of the first column. Okay, this doesn't make sense. Okay, so we can see that this value is standing at the power of 10 to the power of minus 15, which is basically 0. So that means that we calculated the turbulent fluctuation correctly, and also the measurements are valid, yes, of course. And this can be done for all the 3 components, so that we have just zero errors. So, okay, this is just for verification. I can clear this content here. So, for calculating relative intensities, we need time average of these at the power of 2. So, what we need to do first is to calculate U prime at the power of 2. This is going to be meter square over second square, which is also joule per kilogram. Let's keep it like this. So we create 3 new columns. in order to calculate the square of each turbulent fluctuation for each time. So this is equal to the value over here at the power of 2. So we can put this value on the horizontal and then on the vertical direction, so that automatically it calculates the right square of a square value here. So v prime square and w prime square. And then if we pull it, all of these three cells, we pull them in the vertical direction. We get, like, so if we check this value over here, it has to be relative to the second column for v prime at the power of 2. So now we calculated the turbulent fluctuation at the power of 2 for each time. What we need to do next is to calculate the time average of these components. So for each component, now we have u prime square, v prime square, w prime square. We need the time average, which is a simple arithmetical average. Again, so I'll write it here like u prime square. I like a subscript bar over there. This means that this is time average. And this is square meter over square second. And we can do the same for the other two components. So we get here v prime square time average, and the last value that we need is w prime square time average. So we calculate this using once again the average function available in Excel, and we select the correct column. So for u prime is the first one, and then we can pull it also for the other other two directions. So we get this type of values for each of these terms, which are actually the diagonal terms in the Reynolds stress tensor. So the Reynolds stress tensor is we have u prime, v prime, v prime, w prime, w prime, and then on the top here we have u prime, v prime, u prime, w prime, and here we have w prime, v prime, w prime. And this is symmetrical, so also the on the bottom part of this tensor we have the same values. So by doing this, we calculated already the diagonal terms of the Reynolds stress tensor. We were asked the relative intensities U at, which are now easy to calculate since we have everything we need. So u W hat, then we have V hat and W hat. So the first one is going to be the ratio between U prime squared times average over U0.
Shouldn't be square root.
Yes, yes, that's correct. So the square root of, thank you, of square root of U prime squared over U0, which we can do also for the other two directions. Of course, I got this error because I need to lock U0. So these are the results for the relative intensities. Now let me check. I have the solution files. Let me check that these are correct or I've made some mistakes before. Okay, so these are good. So then also right here that these are the relative intensities. So the next quantity that we need to calculate is the turbulence kinetic energy. So for turbulent kinetic energy, which is given in this equation, we need to use U prime square, E prime square, and W prime square that we already have calculated. So we can use that equation as 0.5 times the sum of U prime square times average plus V prime square times average plus W prime square times. And this is K, which is square meters per square seconds, but typically we use the joule per kilogram unit. Are you following? Are you already stuck? Next quantity to calculate is turbulent intensity. So turbulent intensity is over there on the right. So it's the square root of 2/3 times turbulent kinetic energy over U0 to the power of 2. It's a quantity to measure the value of turbulent kinetic energy over the free stream velocity. So this is turbulence intensity E prime, which is dimensionless. So this is the square root of 2/3 times turbulence kinetic energy A over u0 at the power of 2. So free stream velocity, we have it here, and we make that at the power of 2, and so we get this value over here, which we can multiply by 100, or we can just see the percentage over here. So that we get a turbulence intensity of 0.164%. Finally, we need the Reynolds stresses. So we need to calculate these terms for the Reynolds stress tensor. Well, in total there are 9 terms. Of course, if this is a symmetrical matrix, then we will only to calculate 6 terms. We already calculated the terms on the diagonal. So now we need to calculate the other terms, which are the time average of the product between the turbulent fluctuations in the various directions. So what we need to do is to calculate u prime, v prime, then v prime or u prime, w prime, and the last term is v prime, w prime, and these are calculated for each time as the product between the turbulent fluctuation involved. So for the first term we have u prime times v prime. For the second term we have u prime times w prime. And for the last term we have v prime times w prime. So these terms are instantaneous values, so we need to calculate them for all the available measured times. So we can do that by pulling these 3 formulas in the vertical direction. So we'll have now the instantaneous values for the Reynolds stresses. So what we need to do is to calculate the time average of those columns. So that's going to be, let's write all of the terms, u prime, v prime, and w prime, which are the diagonal terms. So as said before, these are equal to the terms calculated before, u prime square, v prime square, and w prime square. And then the other terms are u prime, we can have apart over here, so that we mean that they are time average values. So then what we got here is u prime, v prime, u prime, w prime, and v prime, w prime. And these are, once again, the time average. So the average of the last columns we calculated. So u prime, v prime column is for the time average of u prime, v prime, which we can pull also for the other two terms. Now that we get the Reynolds stresses. So by performing the Reynolds averaging, our Reynolds stresses will look like that. This is the Reynolds stress tensor that we have there. So basically this is the term, this term over here, u prime, j, u prime, I, that is in the Reynolds average momentum equation. Of course, that is calculated with experimental data. If we are, for example, making CFD simulation, then of course we can't do this process, so we need models to calculate this. So, let me check that these results are also correct. Yes. Yeah. So this is the last exercise for today. As mentioned, here is the homework again. So find two correlations in literature or also on books. On Wilcox also there are already some formulation for this mixing length. And secondly, you can return the solution of this problem. So if you don't have any questions about this exercise,